4 times a year. And this one is a special one, which is a little bit out of scope. It's a special team that we already had one last December, implementing these such little LoRa devices here in a workshop, which was much fun. And so today we are looking at more at the theoretical side and what can be done with GnuRadio, which is a very interesting thing we have been seen before. So just I need to say a couple of things before we start, that we will have, or we already have a video stream, and Oleg from the TTN group is providing this video stream for those that cannot come to Bern. And so you may, are there any people already connected to?
4.
4 people,
yes.
So there's a group from Basel that had interest to join us, and they didn't want to travel to Bern. So if anybody has a problem if you're taking pictures or having this video stream, raise your hands now. Okay, then I assume that it's okay. You're not directly on the video as I am. So I don't want to make it much longer. Just about Joachim, you did your bachelor and your master's at EPFL, and you're now pursuing your PhD in the TCL lab, Telecommunication Circuits lab, with Professor Andreas Borg. He had not been able to come because his superior has called him for a meeting tonight, so you can't object to that. And so you will probably introduce yourself a little bit or tell us what you're doing. And I leave the floor to you. Thank you for coming, and I'm looking forward to a very interesting presentation. Okay. So here is Steve.
So, good evening everyone. I'm Joachim Tapparel, so I'm a PhD student at EPFL in the Telecommunication Circuits Laboratory, as said. And I'm working with LoRa in the context of my thesis, that is more generally on low power wide area network, that I will give a brief introduction. So today I will talk about the physical layer of LoRa and its usage on software-defined radio and how we use it in EPFL to experimentally verify some concepts. So today I will give a short introduction about low power wide area networks, software-defined radio, and GnuRadio. So relatively short, but to have some basic idea of what I'm talking about. Then the main part will be about the physical layer of LoRa, such that ideally at the end of this talk, every one of you has a good idea of what is inside a LoRa transmitter and receiver, and maybe also all the parameters that you can be familiar with when you are using LoRa to communicate will have more physical meaning to you. Then a few words about our open source implementation that is on GnuRadio and available on GitHub. And finally have some description of which work we did in the past in the lab and what we are targeting now in the current research. And finally, a small demonstration of software-defined radio. There was already a FM radio list. We could already listen to this FM station, but I will give a demonstration where we can look at them in the spectrum. So hope that will be interesting to you. So let's start with low power wide area networks. So it's the type of network that have emerged in the recent year or past decade that targets low power consumption, long range communication, but only providing a very relatively low throughput. It fills a gap between local area networks such as Bluetooth or Wi-Fi that we're all familiar with, and cellular networks, so for the cellular generations. So providing a lower throughput but a range similar to cellular telecom. It's become quite popular with all the IoT applications, so smart cities, smart farming, etc. So in the recent year, there are really been a lot of devices that have been developed, and a few technologies, the pointer won't be great on screen, but a few technologies that have emerged with LoRa being one of the main or the most used and deployed one nowadays. So we're focused on LoRa, as you could guess from my title, and it's one of those LP1 network technology. It uses the unlicensed ISM band, so you don't need a license to transmit after frequency. It's similar to Bluetooth or Wi-Fi. It has a low power consumption, targeting battery life in a decade ideally, and it's a communication range that reach multiple kilometers, so that's quite high targets. So how does it try to do that? First is to giving up on high data rates, so it's really for low amount of data that gets transmitted, and it uses, the main peculiarity of LoRa is its modulation, so how it transmits the information using the electromagnetic waves. So you might have be familiar with amplitude modulation or frequency modulation, so like FM radio stations, which one would change the amplitude of a signal to contain information, one will change the frequency of the signal, and LoRa will have some form of frequency modulation that I will have more details, but that's a very peculiar way of encoding information, and that's what we wanted to study in our lab. So how do we study it? So having a prototype or something that really transmits to verify that it works in the real world is very important for us, and software-defined radio is a type of radio that is very versatile. It's just take a signal that is in a high frequency, put it back in a low frequency, and then you can process it using any usual computer, or here an example with a Raspberry Pi and a small SDR USB stick. So that's very convenient to build prototypes, and that range from small USB sticks that are 20 francs to racks or more advanced hardware that can be as expensive as we want. We've become some very cool hardware from NVIDIA that is made for a new generation of cellular, where they want to have some part of the network implemented in software. Now, for us to program them, we are using GnuRadio, which is open source framework that is convenient to build real-time processing systems. So it has a programming flow where you would connect unitary operation together to make similar to a block diagram or flow graph. And from that, you get automatically some code that is generated. If you don't like the user interface, which is the case of a few people, then you can directly go straight to the C++ code only. And then there's some GUI that is nice to develop, to quickly develop things, software. And some of the most expensive, that's more on the expensive side of software-defined radio, they have, you can build your own hardware accelerator directly in the signal path. So that's something very cool that GnuRadio also integrates. Now, for focusing back on LoRa and more details on how it transmits and receives signals, we have seen an overview of the transmitter. So it's called a bit, or it uses a bit interleaved coded modulation, and that's each one of those words should make sense after the talk. So I'll let you follow along. And it's relatively simple. So there is nothing. Okay. Yeah. Yeah. So it's a relatively straightforward way of transmitting, except for the modulation, but everything is relatively simple as it needs to run on low power hardware, so nothing too fancy, and really it is really in there. So I can go through it today, and you should all be able to follow what's going on. The receiver, it's basically the same. You get one-to-one one-to-one match. Just every block of the receiver will undo or use what the transmitter did. So quite also something quite simple to follow. So if we go before going to the stuff, to get the idea of what's going on through the transmitter and receiver, we'll just follow 1 byte of data that gets through each step, and hopefully at the end we'll get it back. So the first thing that we do is to remove any pattern in the user data. For example, here we transmit a byte of all 1, and it's something that we don't want or don't like to transmit. We want data to look random. So a simple operation that we do in the beginning is to do XOR, so just 1 and 1 will give 0, 0 and 1 will give 1, and 0, 0 will give 1, so just a simple mathematical operation that takes the input bits and then makes them look random. Then we do that for the full payload, what we want to transmit. We prepend a header, so that contains some information about the transmission that the receiver needs, for example, the length of the packet or the code rates used for the encoding. We append a CRC, that's a cyclic redundancy check. It's a form of a hash that allows you to know if your packet is completely correct at the receiver. You can't correct based on it, but you can know if you need a retransmission, if your packet is valid or not. So from there, we can hold the bits that are contain information, so the information bits, but we want to add some form of redundancy. So every time you have a transmission over the air, there is a chance that some of the bits you receive will be wrong. So you have some of the bits that are 0 instead of 1. And to not have to retransmit everything, which is quite costly, we prefer to add some more data that will help correct errors. So what LoRa does is it's called a Hamming code. So it's a type of code where you can build the parity bits from your data, you multiply it with a small matrix that is viewed here and do a modulo 2, and you get a bunch of additional bits that you want to transmit. And with that, we have all the bits, so data bits and parity bits that we want to transmit in our frame. Now, I said it was a bit interleaved, so now we are at the interleaving. It's a way to distribute the information over a longer time of transmission, so that if you have an error at some time, it will not impact the same data, and that will help greatly for the error correction. And LoRa uses a diagonal block interleaving, which is given by this formula, or intuitively you can look at it. You get a block you want to interleave, it's rotated by -90 degrees, then there is a circular shift of every row, and you get the same data but in a different order. From those new order, or from those bits, you can map them to a decimal value, because I will see just after, the modulation is not binary. You don't get a choice if you want 1 or 0. You get a choice between decimal value or hexadecimal values.
So, quick question.
Yeah.
Where did those extra bits come from? Like on the first row, 1, 0, and then 0, 1, 1, 1, 0. Where did that come from?
The one that are in gray?
Yeah.
Yeah, it's just I didn't write it all the time. I just took I followed or first we follow 1 byte, and that byte is here. The
Okay,
rest
so those
is
are other bytes coming later?
Yeah, or in this case is the header, so it will be the
Okay.
information. And I just wrote them in this one to match the hexadecimal value. Yeah. Thanks. I don't hesitate to enter. Yes, so we get a bunch of value we want to transmit, and now we want to send them over the air, so we need to send some form of signal. And for that, LoRa uses chirps, so chirp spread spectrum. So if you look at this, that's a spectrogram, so we have the time and the frequency. Every LoRa symbol, we start at a given frequency and then increase linearly. And that is a bit useless because we just transmit zeros. But you can modulate those symbols using this equation, which is a bit difficult to intuitively interpret looking at it, but it's very simple. It's just change the starting frequency of the chirp, and then once the chirp reaches the higher part of the bandwidth, you just fall back to the lower part. So that's how LoRa encode information to transmit it. Now we can transmit it, and that was a recording I made of a LoRa transmission where you can clearly see the different chirps. So it's good. Now we have transmitted the signal, we want to receive it. And the first step is to get from that signal that is electromagnetic wave back into values that we can, value of bits or bytes or decimal values. So LoRa, to demonstrate LoRa's chirps, there is a very efficient way to do it, and it's one of the key aspects. Is the first operation you can do is you take your symbol, so 1 chirp, and you multiply it with a chirp, but this time this one is going downward, so it started at a high frequency and the frequency that decreased. And this operation has the effect to gather all the symbol energy into a single frequency. So now the whole symbol has just a pure frequency. And what you can do with it is computing a discrete Fourier transform. It's a mathematical operation that gives you which frequency are present in your signal. So it's just representing the signal in a different way. And in that case, we have only one frequency. So the discrete Fourier transform will hopefully give you only one peak. And conveniently enough, the location of that peak is the symbol that was the value that was modulated. So you look at the maximum and that gives you what was transmitted. That's the usage of that discrete Fourier transform is very nice, and that's one of the key aspects why LoRa is energy efficient and can transmit at low power, that you get a maximum likelihood detection or optimal detection that only has a complexity of n log n, so it's something that is quite efficient and to get a maximum likelihood detection, which is not possible with other modulations. Now, I went a bit fast because the real world is never as happy. There will be a lot of impairments. When you receive a signal, you won't receive something that has a clear peak like you can see here, but the signal will be affected by hardware non-idealities. So for example, the carrier frequency offset. So your transmitter and receiver don't have exactly the same frequency. Sampling time offset, they don't know when to start sampling. So what you receive could look like that, but it's even worse because you will have noise on top, because just your receiver chain has thermal noise because you have electronics there. And now it's much more difficult to find where was your symbol there. It's here, so it's not even the maximum anymore. So to do that, I won't give the details here, but there are a few steps that you can estimate and compensate for the two impairments. And after compensating what we call subsample, that's the name is a detail, but that's you can gather back the energy into one bin, and then you can find the correct location of the bin by two additional compensation. So it's a not trivial process, but it's something that you need to do in order to get back the data you want. So with that trick, synchronization and then the modulation, yes.
Are those the only two parameters you need to figure out, STO or CTO?
It's the main problematic.
Okay, so where is it in the shift,
Yeah.
time shift, and also the frequency shift?
Yeah, gathering the energy into one bin
Okay.
and then moving it in the correct position.
Okay.
Then there are other impairments, but those are, without that won't work at all. Yeah, so with that we can demodulate all symbols, get the value, then the demapping, that one is a bit boring, it's exactly the inverse as the interleaving is the inverse of the interleaving, so it's just circular shift rotation. Now what is more interesting is the decoding, because we added redundancy in the transmitter, we encoded, so we use more energy to transmit, so now we want to use it in a smart way. So what LoRa uses is the Hamming code, so you can represent it with a Venn diagram like that. So you get parity bit 0, data bit 0, so you have 8 values that correspond to the 8th position in one row. If you fill the 1s and 0s that you receive inside, and you do an XOR operation for each circle, so you just sum everything and do a modulo. If that gives you a 1, that means there is a problem, a 0 means it's all fine. And in that example, by very lucky, there is one error, so it's good to demonstrate. You can check what is the intersection of all the red circles, and if you flip that bit, then everyone will agree. Everyone will say, okay, I'm fine with that packet, or that byte. So that's how you correct error, is just you assume there is at most one error, and if there is, and then you just compute the intersection of those circles. Then you can decode for example, the header, so that's for the extra bit that were added in green, they mean something, it's the header. And yeah, so you do that for your all packets, and you hopefully have all your data. Now, we need to undo the whitening, so the first operation that we did, we do it again, because if you XOR twice the same sequence, it will not have any effect. So we get back to our all ones value. Now we want to know not only if the all one or the first byte is correct, but the whole packets. And what you can do, you compute the cyclical non-seal check on what you receive. You compare it with what was included in the packets, and if both match, that means you have high probability that you have a completely correct packets. So now it's the end, so I hope, or the end of the reception.
How do you synchronize the pseudo-random, or what is the special formula to generate?
It's generated with a LFSR, linear feedback shift register, so it's just very simple. Very simple thing
you have to
implement
synchronize both ends.
They just start at the beginning of the frame.
Okay.
So there is a phase that I didn't mention here in the beginning. There is a preamble, some sequence that is known by the transmitter and receiver, and when they detect the preamble, they know, okay, I need to start that pseudo-random sequence from the start again. So that's how they both use the same.
And how is it random?
It's pseudo-random, so it has the statistical property to like it's random, but you can, if you generate here and at another location, it just to have the same sequence of 1 and 0.
Okay,
But if you look at it, it looks like a random sequence.
and the starting value of the seed is?
Yeah. I think it's all 1 for LoRa.
Oh, they start all ones. Okay.
Yes, yeah. In a cellular, there is also some pseudo-random sequence where, for example, the seed will be user dependent. But for LoRa, it's just everyone use the same. Yeah, so we get our packets. Now we've implemented on all those operations and a few more, but if you look at the block diagram that we've talked and the GNU-Radio implementation, so that's what a GNU-Radio flow graph look like. So you have a sequence of operations, and they match then one-to-one with a few exceptions. For example, checking the CRC is its own block. But that's useful if you want to make some changes or play with it. But we have also a simplified version with just one block that you can use for the full, it's your LoRa transmitter, is that block. Then to use it, it's quite simple. You choose if you want a transmitter or a receiver, or both, and you connect a block that will represent your radio. And it's just, if you have a HackerF, then you take the block that HackerF provides, or not HackerF, but that you find in GNU-Radio by default. And for the transmitter, you just need to add some message that you want to transmit. Then you fill some parameters. Maybe it's too small for people in the back, but it's the standard LoRa parameter, like the bandwidth, the spreading factor, the code rate, etc. And if they match the transmitter and the receiver, then you get your data. And that's what I will try to show in the demo. And yeah, that's also work with a commercial LoRa chip. So you can use both two SDR to transmit and receive, or you can use commercial chip to transmit and receive with SDR or the inverse. Now, yeah, it's on GitHub, so if you want to play with it, don't hesitate. And we've then also made some experimental verification of the implementation to be sure that it works as expected. And it's successfully been used in a few papers already with many different topics that relates to LoRa, that goes from wireless sensing to jamming or multiple access studies. Now, for what we're doing, because in a group we want to use LoRa, but not just use as is, we have mainly been focused on improving the scalability of LP1 networks. So as it becomes more and more popular, there are more and more nodes that use that technology. But there is one main issue with those type of technology, is that to reduce power consumption, they use very simple scheduling mechanisms. So basically, when you want to transmit, you transmit. You don't have to respect any schedule or whatever. And that's a problem, because when two people transmit at the same time, at the same frequency, then you have collisions, and the packet or the information might be lost. So that's a real issue, and it's known that for pure LoRa, that's the name of just sending whatever you want, that it's a very bad way of using the resources or the channel to transmit. So, for example, this picture don't need to too many details, but for example, with a pure LoRa, you would have only 18% of the time at most that you can use for valid transmission. The rest will just be corrupted by two people talking at the same time. And there are some mechanisms to improve it, but they would require synchronization between the transmitters, and that's something we want to avoid. So for us, we've evaluated how much of a problem it is, or collisions is an issue. And the difference, for example, from Wi-Fi to LoRa, is that as it has a long range, you have a lot of devices that interfere with yourself. Unlike your Wi-Fi, that the neighbor 2 house further will not hear it anymore. So that creates quickly a lot of collisions within the network. So we propose some methods to resolve collisions. So normally, if you have two people that speak at the same time, they would either be both lost information, or one is shouting loud enough such that you hear at least that one. But also we focused on recovering, for example, both users that would transmit at the same time. Now it has some limitations, so what we want to do is to change to work now on the network architecture, so the way the data is processed. And that's a concept that we borrowed from cellular networks that is quite popular for 6G or 5G already, which is called centralized radio access network. So it's a way, or instead of having base station that will receive your signal, demodulate, decode, and just transmit the user data through internet, you just, similar to a software-defined radio, you get the high frequency signal into a low frequency, and then you just forward it in somewhere else to be processed. That has a few very nice benefits. You can process the signal from different receive locations, so that's great to have. You can combine the signal to interference cancellation. It's also easier to have coordination between the different base stations, which are called remote head in this context, so the simpler version of a base station. And yeah, you can share resources and have a network function virtualization, which is also a hot topic for future cellular networks. So what we've done is we want to make a testbed to verify that the prediction we made with simulation are valid in the real world. And for that, we've built a platform that is composed of a software-defined radio here, Raspberry Pi for control, and the GPS chip to have synchronization between the different remote radio heads. We have 4 gateways that are deployed on the roof of EPFL. They look like that. They are closed. And here is an example of measurement of the received power, something similar to the received power at one of the remote radio head when someone, which was mostly me, was walking around. So yes, that's how one measurement will look like, and then we can extract statistics and make record that database for further processing. So thank you. I have a demonstration. I hope it will work. And if you have some question already, maybe you can do it now, or I ask after the demo. After.
So the ISM bands, plural.
Yeah.
Which ones are what are their limits, or how much is it for? Like, is this a European, North American band, or is this something else?
Then, if you want to use LoRa, they used in Europe the 868 megahertz,
Right.
and US 915.
Okay, so that's what you mean by bands.
Yes.
Okay.
Yeah. But there is also some version of LoRa now that use the 2.4 gigahertz, the same as old Wi-Fi.
Okay.
Yeah, it's just they use whatever is free.
All right.
And what's the bandwidth of this chirp, one chirp?
It's between 125 kilohertz to 500 kilohertz. So it's relatively narrow compared
There are
to
multiple channels available, or is just
you get
one?
LoRa 1. There's 3 main, I think up to 8 that are defined. That one I'm not sure, but there is at least 5 channels that you can use in one beside another.
And how are the channels chosen? How do the devices choose which channel
There
they
is
use?
to transmit on the ISM bands, you can do it for free, but there is some restriction to use that are in place. There is, you cannot transmit more than 1% of the time. So if you transmit for 1 second, you need to wait for 100 seconds. So if you transmit in one channel for too long, then the next transmission you switch to another channel. Or you can also...
Okay, that's per channel, there's 1% per channel.
Per channel.
Okay. You randomly choose which channel you transfer.
Yeah, usually, or the simple way is to just alternate.
So the receiver has to listen on all of them.
Hmm?
The receiver has to listen on all of them.
Yes. So a receiver will have, depending on all spreading factors, so the chirps, they have different slopes based on different, that's a parameter that you can use. So the receiver needs to listen to all spreading factor and all the channels that are interesting. So that makes a lot of receiver in parallel. Maybe 64 in a gateway.
Okay.
Yeah, with your receiver implementation in GnuRadio, can you listen to more than one channel at a time, or is it one channel?
The implementation, one row will be for one channel, but then there has been people that are just duplicate the row. It's in the graphical interface is copy pasting. So I've seen some implementation using multiple.
You said a Raspberry Pi, is that running this GnuRadio, or is that?
Yeah, the one on the roofs are running GnuRadio.
Okay, does your Radiohead use GnuRadio, or is it just hardware?
They use GnuRadio, so
but not the full.
Not the full receiver, just simple signal detection to not stream data when there is nothing.
Okay.
But it's in GnuRadio, but for example, not through the graphical interface.
And then, so is the Raspberry Pi maxed out? What's the compute?
No,
what's the
it's
compute level?
it was I think when it's running, it's 20% of one core.
Oh. Okay, so even smaller devices would work as well.
Yeah, for one receiver chain is it's not an extreme load.
Okay. Thank you.
Yeah, then that's also LoRa has a low bandwidth or narrow bandwidth, so you don't need a high sampling rate. So that's quite practical for or convenient for software-defined radio because you don't need a very performant hardware to run it.
What's the throughput in bytes per second, or kilobyte or megabyte per second?
Good question. That one is in the range of kilobytes, but then I don't know with the 1% duty cycle how much that reduces it. But the application is more having a few bytes per minute that would be useful data, like sensor that would measure temperature, CO2, or some small variable.
So it allows kilobyte per second, but you realistically only need bytes.
Yeah, because you don't want to transmit for one or for multiple seconds. Because you will, the longer you transmit, then the more energy it loses. And most of the applications I've seen are more interested in having a low battery consumption. So if you have a few kilobytes per second, but you transmit 1 millisecond, then it takes you a few bytes.
And who does the regulation of the different bands? Because you said it's long range, so I saw something with 10 kilometers and so on. So it's not like Bluetooth, which just has a few meters, which you do not need to regulate. But I guess you need to regulate stuff that has a range of several kilometers.
Then you have a limited power that you can transmit. That was the second thing. That was you can only transmit at a certain maximum power. So what you receive at 10 kilometers is much below the noise floor. So you really receive a very little energy, and you can get it back because the chirps will last a long time. So you accumulate energy for a long time to then get your value. So I don't know how the regulate or how I think it should be something from the Swiss government measure it, but I don't know exactly how they would guarantee that no one exceed 1%. I don't know.
It's not. It's not in the device itself. It's left up to you to respect the 1%.
Yeah, or
I guess. Yeah.
you can, if you want, you can do more. Or
I mean, the device that you buy, the LoRa devices, do not restrict you to
No,
send more.
no,
But
you
then
can
you're
keep it.
conflicting with the law, and you have Babcom taking your stuff away.
Yeah, I don't know how much they monitor that. Certainly, if you transmit in the same frequency of a Swisscom base station and at a high power, they might notice it. Say you paid for the license, but yeah.
Maybe I can just add something. I think usually or sometimes the stack itself limits the BP cycle. So sometimes
Okay.
it's you make sure you can't transmit more. But I'm sure there are also
Yeah, you can modify the
devices
stack.
or of course yours, but which don't limit it. But
You didn't implement that in your new
No,
radio.
because that one is only the physical layer,
Yeah.
and it's when you if you install a standard LP LoRa 1 stack, then the stack makes you respect the 1% duty cycle, but yeah, it's open source most of the time, so you can always tweak if you don't want to follow the yes.
So if you use a Raspberry Pi for, I don't know, 70 francs or whatever, and an RF chip for another 10 or 20 francs, I'd like to see that, but that's quite a large investment versus just a chip from a Semtech chip. What's the use case that you could see, besides your research, is there a use case you could see for adding all that hardware to get this functionality?
Yeah, for sure that's not the same. Also, the power consumption is not the same. So that's why probably Semtech.com at us saying, don't do it open source, because that's not and that doesn't compete with when you buy a low power chip. Then the use case end node would be only for if you are a radio amateur and you want to have your own stuff and know what it is. Aside from that, it's more for the base station. So a gateway, a LoRa gateway that you buy will also have some cost to pay, to buy. So that may come in the same range, but that will still be for people that like to play with it, or that's part of a hobby where you would like to build your own point-to-point radio communication, and you want to do it open source, or you want to dig into what it does and how it works. So for me, it's really research because you can make modification to it. Yes.
As far as I've heard, Swisscom is using LoRaWAN to switch on the lamps at the street. That's 1 byte, and then it's on, and they get some money of it because the light sensor seems to be more expensive, or nobody wants that. I don't know.
I think Swisscom is limited you to send 144 messages per day.
Then that depends on how the network provider that can fix such limit that they won't route your traffic anymore after that.
It's about 1 message per 5 minutes at most. And then you respect the duty cycle is
Sufficient.
is measured on the hour.
Yeah.
Just to add why you would use an SDR is if you want your base station to be future compatible. You just can change the code and it will still be able. That would be one application, but I don't know if that's in the interest of the company. So,
Yeah, that goes with the move of cellular network to use SDR to have a photoproof data center or central processing location. For LoRa, I'm not sure how much it will change,
yeah.
but software-defined radio in general, sort like that, like for FPGA compared to NASIC. Maybe I will go with it. I don't know how much time it's.
Yeah, you should just go on. We have 1 hour for all for all.
Maybe some question will pop up. Okay. So I prepared a few just example. First would be to talk general about software-defined radio and see a bit how much different things you can do with them, which is.
Can you mention the prices as you go?
Yes. So that one was 150 a few years ago. Now it's 400. They make the version 2. Yes.
That's Lime.
That's the Lime
Lime
SDR
Mini,
Mini.
or
Yeah. Yeah. So unfortunately, not at this price.
the one that I've been using to stream the radio, the FM radio, is about $10.
Yeah. I
And
have
for $40 you get the whole set, including antenna and so on. So
Yeah, I have. That one is a USB stick size, more expensive, but it does transmission and reception. The one that you have is, I also have a different version of the same chip, and that one does only receiving. So here it's a software that is it's open source, but it's a software to software-defined radio where you can visualize the spectrum, and here I would give a small intuition how you can see the spectrum, see what's going on, and how versatile it is, because usually when you add a radio that is not a software-defined radio, you have some frequency you can listen to, and that's only for that frequency, but those have really a wide range. So for example, here I would go and listen in the range of Wi-Fi and Bluetooth, so the ISM band in 2.4 gigahertz, and we can see, for example, here someone receives email right now. So you can see here it should be Wi-Fi frames, and there is probably a bit of Bluetooth hopping around, so the small, not too much, the small packets or the small parts jumping around our Bluetooth messages. Then we can go to the radio or FM stations. That is I'm sorry for people online. It was thought for them. And maybe I can find okay, FM station are not popular in Bern. Which frequency were you? But you can probably, if I straighten out that antenna, very high tech, have some, that's probably an audio signal, so I'll try to be, yes, so you can easily look at it, find where there is a radio station, and yes.
Is everything FM, including Bluetooth and Wi-Fi?
Bluetooth is GMSK, so here it's only for analog FM.
Well, if you listen to radio, that's FM.
Mm-hmm.
But if you visualize the Wi-Fi packets and the Bluetooth packets, which you just did a minute ago,
Yeah.
this is also FM, or is it just some other thing in this frequency?
Some other, it's a digital modulation. So for example here, you can, if you know what a sound or music spectrum looks like, you can directly see it here. So it's analog, you get every value. Bluetooth or Wi-Fi, they have only some, if I'm not mistaken, Bluetooth is GMSK or GFSK, but it's just, you get two frequencies that it will jump from one frequency to the other. But then you get two choices, and it needs to have some demodulation, decoding, and that's, for example, DAB would be digital. So either you listen, you hear your radio station, or you don't, but you don't hear like here, this one that has a little bit of.
Can you also listen to medium wave or police broadcast or air traffic broadcast?
I think it's not legal to
I don't know.
look at it.
I don't know.
Police is not
It's not legal to listen.
anymore in Switzerland.
I thought it just had their own frequency. What about air traffic?
You can have AEIS, I think it's the one for the plane. I know some of the examples with software-defined radio is to listen to those messages. I think those are okay. But yeah, physically you can do it.
Okay, medium wave?
Which is which frequency range?
It's in the
400 kilohertz range about, I would say.
That one depends on the software-defined radio. There are some that go up to DC, so there is a direct conversion, but most of them would have a minimum frequency in maybe a few.
You don't
few
see it
mega-
here.
So here, that one cannot go that low.
Okay.
But you can go to 433 megahertz.
Yes, that one can maybe 6 gigahertz. So we were.
So I have a LoRa transmission going on over there on 433.
400.
Can you catch this?
433.
I don't know exactly what frequency. It's
There is
every second there's a packet.
Yeah, that's probably that one because it looks strong.
Nice.
And if I reduce the sampling rate, see it. Okay.
So that's
That-
LoRa packed.
Yeah.
It's just one value is being transferred. One value every second. It's a
Then
counter counting up from.
Yeah, then I can turn on mine and
it's really good.
depend on the spreading factor. So here it's just that the chirps that we talked about are too fast to be plotted as chirp. They just look like a full line. But if with a larger spreading factor, so your chirp lasts longer in time, I can open that. Oh, hopefully everything goes well. I plug it in and it should start. But I'm on the 861.
So can you say how long it's transmitting, or can you say this? Can you figure out the spreading factor?
For that, this tool is generic and it doesn't support it. But here, then it's one of I send two signals. I send two signals. One is a short spreading factor 7, so we see a small pulse, and then spreading factor 12. But they send the same information. So there is really a difference that the real-time transmission. So there is really you transmit for more than a second, and there we can see the jumps. Now this software is demodulates FM and AM, I think, but it's not planned for LoRa. So for that, we can move to GnuRadio. And here is a simple flow graph that I made for a receiver. So you get the block that we made, that I mentioned before, with the different parameters for the reception. Lime SDR source, so that's just to say I want to use this radio. Then a low-pass filter, that's something that limits the bandwidth we want to use, and it's just there because I want to plot it in a nice way. But if we start it, we should initializing the radio. Okay, so now we also have a view of a spectrum, so we see the chirps. I have more time to prepare for this one to look nice, so you can clearly see the chirps. And on the top left, you see messages that get received, and that's the beginning of a digital telecommunication book that you will get after a long time. But so only a few words like that will already make quite long packets for the larger spreading factor, which is when you want to transmit the further away. Yes?
I see the preamble as the first, I don't know, 12 lines or whatever, but there's also this blob, the blob that comes between the packets. What is
That's
that?
the counter from
Oh, is it?
No, I'm on a different frequency. That one is I sent both to show the difference of time for transmitting the same.
Okay.
But so there is the same content of information in the small blip as in the full one. And then you can clearly see the for those who know the preamble of LoRa, which gets 8 repetition of the same chirp and then 2.25 data in the other direction. But yes, so that's for the reception. I also that works also easily with just using a cheaper one. So here is the same that was tuned to the FM. So if I plug this one instead, and then wherever, it's so I already prepared it. So you just plug 2 different blocks or 1 different blocks, and the low pass filter is just to make it look nicer, you can connect it to the GUI to see it, and also to our receiver block. And again, it should work as expected. Yes, so this time there is just a small window, but it's just a detail because of the sampling rate that are supported by the radio. It's simpler to have, you don't need to look at such a wide spectrum to decode the information that is in the middle, but you can stop sending.
So this visualization component that has been implemented by you, or is it standard?
No, this one, it's something you can install. It's not in the basic GnuRadio,
Okay.
but you can install to run on GPU or Intel CPUs to have a better.
But that's a special LoRa visualization
No,
component.
that one
or-
is if we transmit, it just shows the spectrum. It's
Okay.
a general box waterfall diagram. That looks better than the default GnuRadio that you.
Mhm. And what is it called?
GR phosphor.
So
Yes.
these blocks that you say you can install,
Hmm?
do they have like a library, or
Yeah.
is it,
Yeah, there is GnuRadio has some web page with all the different blocks that have been somewhat tested or that are used, and then installing them is relatively straightforward. It's made for making block and sharing blocks, so it's five line you type in the terminal to download the library, build it, install it, and then the block will just appear. Like for example, this is the block that makes the nice visualization. Just install a new module and it's
Can you make it appear with a little bit larger so we can see?
Yeah.
Phosphor sync. Okay, that's the one.
Yeah, and that's then
And where do you get it from? The phosphor sync?
from the GR phosphor repository.
Okay, it's just somewhere
it's
on
on
GitHub.
Git's, And then there was a part where I transmitted, but the USB port is blocked by the HDMI cable. So I think you have to believe me that it works.
So the only thing that it comes from your lab is this LoRa RX.
Yeah.
And it's a C++ stuff that you compile, you can download and compile.
Yeah, to download it is then it's downloaded from GitHub, build, make install, and then it should show up in the block.
What do you do if in make
Does
it's
it
an
work?
error? There's an error.
What's the issue on Git? there are some issues that can arise, but if you are using Ubuntu with a standard GnuRadio installation, should not.
I'll just try it this afternoon. I got an error and I quit.
Yeah, I'm sure we can work that out. But yeah, having some issue. There are some issues posted on Git.
user error?
Probably yes.
Yeah. So, thank you for listening.
So thank you very much, Joachim, and we'll have something for you. Just to compensate all your efforts, and thank you very much.
Thank you. Pleasure.
So I think we have enjoyed, and if you have any other questions, we can still, you're still around for the apéro. And we decided to go have a pizza afterwards, so if anybody wants to join us after the apéro, you're invited to come with us to the pizzeria. Just two announcements. First one, we will have another main talk, probably end of February, or beginning of March, and you're invited to join us again. It will be a different topic. The topic has not been decided yet, but if you have subscribed on our mailing list, then you will be informed as soon as we have decided what's going to be, and this will be here. And then there's another topic I want to let you know. GNU Tapparel is organizing the second workshop on Wi-Fi Halo in Winterthur on the 22nd of January in the afternoon. If this is a topic that is of any interest of anybody of you, then feel free to keep in touch with GNU and we'll tell you where it happens and you get the announcement. This is not being distributed on the Mint Talks, it's a separate topic. It's very specific. You might not know what Wi-Fi Halo is all about. It's a standard from 2017, but there's still very little use, but it's a very interesting topic, and we have several student works going on throughout Switzerland and Austria, which will be presented at this workshop. So thank you for coming and having this very interesting discussion also. Now we have this little apero. Please enjoy.